Um,
Are you just through all of this?
all right, there we go. All right, don't be concerned. This isn't a real fire. All right? Put the fire extinguisher down. All right, so we're going to be talking here about heat energy. All right. So everything in the universe, when we think about everything around us, we sort of can break everything into one of two categories. Everything is either matter or energy. So obviously matter, you know, your desk is made of matter, your pencil, your notes, and you, and even the air in the room. That's all matter. It's something that has mass and has volume. It's physical material. But there's also then in the universe energy. And energy includes things like light, sound, heat, electricity. These are forms of energy. And when we think about energy, we often put it into two categories, kinetic energy and potential energy. And we'll just briefly mention this now, something we'll talk more about when we get to sort of physics and motion machines. But when we talk about kinetic energy is moving energy. Energy of moving materials, moving molecules. And so, an example, if we think about water moving in a stream, that has kinetic energy. The molecules of water are moving from one place to another. That's kinetic energy. And that's as opposed to potential energy, which we think of as sort of stored energy. Energy that could be released at some point, but it's stored up. And so if you imagine water behind a dam, it's being held back. That has potential energy. When that water is released through the dam, that potential energy is transformed into kinetic energy and can be used to generate electricity or do other things. So those are sort of our two types of energy that we often talk about. Jonathan?
I'm ready to do conservation.
Oh, you are? All right, conservation. So there we have what we call a law. I think we may have mentioned this. The law of conservation of matter and energy. It applies matter and energy really, although we're saying they're kind of like two different things, they really are interchangeable. Matter can be converted to energy, and that's what we know. So the law of conservation of matter or energy has three parts. They apply to both matter and energy. Give me one part, Jonathan.
Energy and matter cannot be created.
Yes, energy and matter cannot be created.
Matter and energy cannot be destroyed.
They also cannot be destroyed. So what the heck can you do with matter or energy?
You can change the form.
Yeah, they transform from one form to another. So energy and matter, for now we're really talking about energy, cannot be created, cannot be destroyed, but can be changed in form. Cool.
So like potential kind of like stops it.
Well, potential energy is sort of stored up energy that can be changed into kinetic energy. Yeah, so we can transform, light energy into electrical energy. How? Yeah, using a photovoltaic cell, using a solar panel, can transform light energy into electrical energy, electricity. So these forms of energy we can transform back and forth, but we're not creating new energy, or we're not destroying energy. It's just being transformed from one form to another. All right, so let's talk about heat as a form of energy. That's what this unit's really about. And so you guys told me earlier, heat is created by the movement of molecules, the vibration. Molecules, even though you may not realize it, the molecules in your desk, they're moving. They're vibrating back and forth. They're staying in a regular pattern, but they're vibrating. And as your desk warms up throughout the day, as the room warms up, they're going to vibrate slightly faster. And if it cools down, they vibrate a little bit slower.
If I hit them, will they move faster?
Not really. So the other thing you guys told me as we answered today's question, you said that when you heat up matter, it expands, it gets larger. So when temperature increases, the molecules vibrate faster and they spread farther apart. And so nearly all matter expands when its temperature increases and contracts when its temperature does what? It decreases. Now you notice I said nearly all matter. Why did I have to add that nearly? What does that mean? Bianca?
There's an exception.
Yeah, that there's an exception, and a very important exception. And without this exception, you may not have life on Earth. What is the exception? What is a substance that in certain instances, when it's heated up, it doesn't expand but contracts? And when it's cooled down, it doesn't contract but it expands. What substance is this?
Oh,
Veronica?
water.
It is. It's water.
Wait, water cools it.
So water, if we look at water around the freezing point, water that's very cold, slightly above freezing, liquid water, okay, has a certain density, okay, a certain volume for a certain mass. When that water is cool and then solidifies and freezes and forms ice, it doesn't contract. Even though we're making it colder, it doesn't contract. But because of the crystalline structure of ice, cooling it from liquid water to ice, it actually expands. It's larger. The density decreases. And so what does that mean about lakes around here right now? Great Lakes are almost completely frozen over at some points. One of the most ice cover we've had because of the cold conditions recently. But what does that mean about lakes and how they freeze? Let's imagine that this exception didn't exist, and that ice was more dense than liquid water. What would happen as a lake started freezing? Bianca?
It would freeze and then it would get smaller and then there'd be
So as that ice forms, what would happen?
when it melted, the lake would be cold.
Not quite.
It was like
No? Sachin?
Ice would stay.
Yeah, if the ice was more dense than the water, as it froze, it would sink. What eventually would happen to the lake?
it would flood.
Well, not necessarily flood.
The whole thing would like turn
It would freeze from the bottom up and eventually be completely frozen, the whole lake.
Oh, like when you put water on top of ice or whatever?
Yeah, if you form an ice cube, and so obviously there's nothing's going to be able to live in a block of ice, really. But it doesn't freeze that way. Because the ice is less dense than the liquid water, as the lake starts to freeze, where does the ice go?
Up on top.
On the surface, and that insulates all of the water below. And so in lakes that are of significant depth, you have a layer of ice on top and then liquid water below it. And there's space for life to exist underneath the ice. And so that's an important factor in allowing things to live in those conditions. All right, thermometers have basically used this idea of thermal expansion, and that's how they tell the temperature. Okay, so if you have a thermometer, it's basically just a glass tube filled with some liquid. Okay, usually it's mercury or sometimes alcohol. And so that liquid that's in the thermometer, as it gets heated up, what happens to the liquid?
Goes up.
It expands, and it can only go up in the tube, so it goes up the tube, and that indicates how warm it is. It's marked off and calibrated so that it corresponds to the proper temperature, but that's how a thermometer works. Okay? Does anyone have at home one of those Galileo thermometers where they have the floating little bulbs with different colored liquids, and depending on how warm it is, they sink or float to certain levels? Anyone ever see those? like be on a desk, yeah. And again, it works on those principles that as the liquid inside changes its density with temperature, then some of those sink and some rise, and that tells you the temperature. So as the liquid in the thermometer warms, it expands, goes up the tube, and it shows you the correct temperature. Thermal expansion becomes important in engineering because, especially in like a road surface, for example. And in our area, obviously we can be, well below zero in the winter and 90 degrees or higher in the summer. So that's a huge temperature fluctuation. And just like all matter, pavement, cement, building materials expand and contract as well. And so, like maybe in your house, you may have noticed, like in the summertime, sometimes like certain wooden doors stick. And again, part of that is because of the wood expanding when it's warm, and it's hard to open them because they bind with the doorway a little bit. But same is true of like sidewalks and roads. This is an expand. So often, engineers build in what's called expansion joints. This is in a bridge, and what it is, it's these metal plates that go between sections of the bridge. So in the summer, when it gets warm and the surface expands, those little metal parts, they have room to expand. If they didn't have that room to expand into each other, then the road would buckle. So they have that. In the winter, when it's cold and those that road surface contracts, they can pull apart, but it's not going to leave a huge gap in the road because there's still that overlapping area. Herschel?
So at nighttime when I'm sleeping, I hear like little cracks.
Sometimes, like as the wood expands and contracts, you might hear it. Sometimes, yeah, in driveways or like in a sidewalk, in the sidewalk sections. If you look closely, you'll notice every couple sections there may be like a strip of like foam or rubber in the sidewalk. That's an expansion joint. And what that does is, in the summer when the sidewalks expand, it just compresses rather than the sidewalk buckling. It gives them some room to expand. These are some railroad tracks which were buckled because of that expansion. This picture shows a couple railroad workers. What happens is there's bolts that hold the rails together in a railroad track. And if that bolt breaks in cold weather, the sections of the railroad track can separate. To reconnect them, okay, what they do is they put a rope soaked in kerosene, light it on fire, they put it along the rail. So as that rail heats up and expands, the sections come back together. They can then bolt them back together, and then
What is that
the
dude
rail.
standing on? Like
This guy?
No, the second one.
Him?
Yeah.
Standing on the side of the railroad track.
This was Timoni's wooden table. There's a huge crack in it, but she says in the summertime in the corner.
Oh yeah, so that's it. That's thermal expansion. All right, you guys are going to have to memorize some temperatures. And I would guess you probably know, out of the 8 temperatures, you probably already know 4 or 6 of them. And you're going to have to know them in Celsius and Fahrenheit. We have various temperature scales which we sometimes use. We generally in the United States use Fahrenheit for our day-to-day. When you watch the weather on the news, it's going to say it's -5 degrees Fahrenheit. Around the world, most other countries use the metric system and would then use Celsius rather than Fahrenheit. But in science, what are we going to use?
Fahrenheit.
Celsius.
Oh, Celsius.
We use a metric system in science, so we'll be using Celsius when we collect our data. But Fahrenheit is sort of what we use in our day-to-day. And so, the temperatures don't match up. Okay, so sometimes you have to think about what one temperature in Fahrenheit means in Celsius and so forth. But there's also another scale. We won't really use it, but I just want to mention it to you. It is used sometimes in research, and that's the Kelvin scale. In the Kelvin scale, so as we cool down, so we said when we heat up molecules, they move faster. What happens as we cool them down? Move slower. Now, if you follow that, theoretically, as you keep cooling something down, what eventually should happen? Molecules stop. And that point at which the molecules basically stop moving, we call that absolute zero. Basically, it's like the coldest temperature you can get. And that's 0 degrees Kelvin is absolute zero. So if you're able to cool something to 0 degrees Kelvin, the molecules stop moving. Now, scientists have not been able to cool anything all the way down to absolute zero, to 0 degrees Kelvin. They can get very, very, very close within fractions of a degree of absolute zero, but not right down to absolute zero.
Well, why not?
Just they're not able to. It takes too much energy to cool things down. So go.
What's absolute zero?
In Fahrenheit, I don't know exactly in Fahrenheit, it's negative 273 degrees
Oh,
Celsius. So you can do the conversion. You know, to convert from one to the other, you can use a formula. Sometimes it's built in your calculator.
is there some component in that?
Not really, because the molecules have stopped moving, so you can't move any slower than that. And there's really not a maximum on these temperature scales, because again, the molecules can always move faster. Grant?
Is there like a fraction of like Celsius to Fahrenheit? Like, how do they do the conversion?
Yeah, it's, I always confuse it. 5/9 Celsius equals 5/9 Fahrenheit plus 32. I'm not exact, that maybe you have it wrong. And then to go the other way, it's 9/5 minus 32, but I may have them reverse. But yeah, you can just use a formula. So the temperatures you need to know. Human body temperature. I'm sure you know it in Fahrenheit. 98.6 is typical average human body temperature. In Celsius,
37.
it's 37 degrees. 37 degrees Celsius.
Wait, do you want us to write Fahrenheit too?
Yeah, write them both. You need to memorize both, and you'll have to know them on your quiz. Now, room temperature, obviously the temperature of a room can vary radically. But we sort of say, when we say something's at room temperature, we're saying around 68 degrees or so. And so that is equivalent to 20 degrees Celsius. So just to give you an idea about, if somebody says it's 20 degrees Celsius out, they're fairly comfortable. Freezing point of water, you probably know both of them, I would guess. What is it in Fahrenheit, Emma? 32 degrees. How about Celsius? 0.
French.
And the boiling point, you may not know it in Fahrenheit, I'm guessing. Sachin?
212.
Yeah, 212 Fahrenheit. And Celsius? Yeah, so Celsius seems to make a lot more sense, doesn't it? 0 and 100.
Yeah, my dad was saying how much easier Celsius is
Yeah.
because it's like we you think it was.
Right.
It's like the ancient.
What was set, the Celsius scale was set with those 0 as freezing point, 100 as boiling point. Morgan?
If the degrees is in the negatives in Fahrenheit, would like say it's negative 12 Fahrenheit, would negative 12 Celsius be bigger or smaller?
It'd be warmer. All right. Now, when we talk about heat and temperature, there's a distinction that sometimes is confusing, and that's what is heat versus temperature. Okay? So, when we talk about the temperature of something, okay, temperature is a measurement of sort of the average motion of the molecule. The average, we might say, kinetic energy of the movement of molecules in that substance. Whereas when we talk about the amount of heat in something, in a substance, that is a measure of sort of the total overall movement of all the molecules in that substance. So it'll be a little clearer in a minute about what that difference is. So the amount of heat in a substance will depend on a few different factors. So it depends on how many molecules there are. So if there's many molecules, it's going to be more heat. Because we're looking at the total energy. It'll also depend on how fast the molecules are moving, on the temperature. Faster the molecules are moving, again, the more heat. It may also depend on the type of molecules, the substance that we're looking at. So temperature is really not energy, it's a measurement of energy. And heat is the actual energy that we're looking at. So by looking at some examples, this probably could become more clear. So there are 3 beakers here. So we look at these 2 glass beakers. So we have some water in each of them. Here I said they are 40 degrees Celsius. Right? We have 100 milliliters of water here, 350 milliliters of water here. So how does their temperature compare? How does the temperature compare? Autumn?
Well, the one with.
So how does their temperature?
Wait, the one with smaller is warmer because the molecules are so close together. Or is it the opposite way around?
No. Nicole?
I think they're the same because the propulsion is like it's like the same propulsion.
Not quite. Jonathan?
They have the same temperature because it measures the speed of the molecules, but
Hold please. So yes, they have the same temperature. Their temperature is both 40 degrees Celsius. The average speed of molecules in this beaker and this beaker is the same. They're moving at the same speed. So they're the same temperature.
Wait, I get to the big, bigger
Hold. So the temperature is the same. The molecules on average are moving the same speed. But if I think about the amount of heat that each of them contains, okay, which contains more heat, or are they the same? Nicole? Yeah, this one, number 2, has more heat. It has more heat because it has more molecules. And again, heat is the total overall energy in that substance. Think about it this way. Is this water fairly warm?
No. Yes.
40 degrees Celsius. Yeah, it's pretty warm. So let's say I wanted to melt some ice that was on the sidewalk in front of my house. Now they have the same temperature, correct?
Yes.
So if I pour the 100 milliliters of water onto my sidewalk, and I pour the 350 milliliters of water on my sidewalk, which is going to melt more of the ice? Number 2. That's because it has more heat, has more total energy, it can therefore melt more of that ice. Or if I think about it another way, what if I have an ounce of boiling water, or I could have a 5-gallon bucket of water that's 80 degrees Celsius, which is going to melt more of the ice? The bucket, right? But which has a greater temperature? My little bit of boiling water. Okay? So again, heat is the total versus temperature, which is the average.
How are they the same temperature if one has more heat?
Because temperature is the average movement. It's just the speed of those molecules. So it's the average speed of these molecules. These molecules are the same. They're moving at the same speed. But this one, because there's many more molecules, the total amount of movement is greater. You have to take in the number of molecules when you're looking at heat. Nicole?
If not like the little glass in the bucket, if like the little glass was extremely hot and the other was like
Very, very, yeah. They could have the same amount of heat if the proportion was correct. Just some more examples. What?
What's the third beaker?
Oh,
It's a muffin.
where's the third beaker?
Oh, I did not get that.
Haven't watched the Muppet Show? That's Beaker from the Muppets. Yeah, that's Beaker. All right, so we have this metal bar at 30 degrees Celsius. If we split it into 2 bars, each at 30 degrees Celsius, how do these 2 bars compare? In temperature?
Same.
Amount of heat? Same. If you compare one of these to this, how does their temperature compare? In the amount of heat? Yes, the big one is more heat. Here we have an example. We have 2 amounts of water. We have this big, huge swimming pool full of water that's pretty cold. And then we have a tiny little thimble of water that's very warm.
What's that under the thimble? What is that?
Who is this?
The dude who sells the
Nicole?
hamburger.
Jiminy Cricket. Yeah, from Pinocchio. Anyway, so that tiny amount of really hot water, even though it's really hot, has less heat energy than this big pool full of cold water. Again, because we have to take into account the total number of molecules. All right. What's that? The pool had more heat because it had so many more molecules, even though it's cold. All right, so we can finish up here. Now, specific heat is the amount of heat it takes to increase the temperature of something. The different substances have different specific heats. Water has a pretty high specific heat. It takes a lot of energy to change the temperature of water. And calories is a unit of energy, a unit of heat. And a calorie tells us how much heat it takes to raise 1 gram of water 1 degree Celsius.
So, next to be the pool, you need to start warming up. Are you actually warming the water? Or are you
Well, we're going to talk about that in a second.
Heat in the water, yeah.
So, heat always travels from a warmer object, a warmer substance, to a colder substance. So here, if I had a 50-degree object touching a 20-degree Celsius object, heat would go from the 50 degrees to the 20 degrees. Now, let me ask you this question. Does your freezer put coldness into your foods?
Yes.
No.
It gives you freezer burn.
No.
You can't put coldness into anything. It takes away heat from whatever you put in there, causing its temperature to decrease. All right, before you put it away, hold on. So if I were to combine 50 milliliters of 20 degrees Celsius water and 50 milliliters of 40 degrees Celsius water, what would the final temperature of my 100 milliliters of water be? 30, right in between those temperatures. For this one, it's 30.